All right, let me try a solution as you guys are getting ready for the exam. It looks like I wrote this down wrong. This was back into chapter 6. So, back in chapter 6, number 45, it's the universal law of gravity, and it says, find the mass of Jupiter based upon the data of the orbit of one of its moons. So, we'll pick one of the moons, but just as a nice review, remember this, that if you have the main object and something is orbiting around it, so this could be the Earth and our moon, this could be, as this problem, Jupiter and one of Jupiter's moons, it could be the sun and one of the planets. But if we realize that it's being pulled into what is often called the parent planet by a force, and we use a capital M and a lower m here, and say the capital M is the big one, the lower m is the little one. So we got the two masses, we got the universal constant, and we got the distance away from center to center, which is also a radius if it's going around. And so that's the universal law of gravity. And if we tie that together with the earlier stuff in this chapter, which says that, chapter 4, the net force has to equal to ma. So net force means we add all the forces, and there's only one, the gravitational force. So this would be the net force. And then times mass, and then we said that the acceleration would be v squared over r, and then directed towards the center of the circle. What's important then to realize is that you could set those equal to each other. And so this was done after Newton discovered, and we're going to get what is referred to as Kepler's third law. A big part of this is to remember which mass is over here on the right-hand side, so you know which one to cancel. And so this is the object going around. So this would be the moon, or the smaller one, and this would be the planet one. Which is why this problem says if you want to find the mass of Jupiter, you need to look then at the velocity of something going around Jupiter, and so one of the moons. It looks like an R would cancel also. And and I'm not sure if we should do this in 2 steps or merge them together. Maybe I'll merge it together. But the velocity of the moon going around would be 2 pi r over the period. I say that because if I grab your book here and they say, okay, look on the chart, if we look here at Jupiter, you'll see they list the parent as Jupiter and the satellite, and here's the 4 main satellites, and so we'll just take Io as the first one here. But they give its radial distance and its period, so they don't give velocity. And so that's why I need to take a step here and get rid of velocity and change it into radius and period. So this is the circumference, 2 pi r, and t being the time to go around. So this would be g and m over r, and then velocity squared would be 4, because 2 squared is a 4, and then a pi squared, and then an r squared, and then a period squared. And then if we rearrange this for m by itself, by the way, this is called Kepler's third law. But if we get m by itself, we would have a 4, a pi squared, an r cubed over here. And in the bottom, we would have the gravitational constant and the period squared. So then, I think is what they're saying here is let's give this a try using the data of one of the satellites. And so again, I'll just use Io. So taking the planet, or the moon, Io, it looks like its average radius of orbit in kilometers, that's important, is 4.22 times 10 to the 5. So 4.22 times 10 to the 5. Now, before I put 10 to the 5, let me just point out that was kilometers. And the K in kilometers means 10 cubed. So I will just add it to the 5. And so there's my unit conversion into meters. That's important because G is the 6.67 times 10 to the negative 11, and that's in units of Newton meters squared over kilograms squared. And meters needs to match with meters. Now, as far as the period goes, well, that's listed here too. It looks like it's got 1.77 days, or this many years. But let's use the days, 1.77 days, because then I'm going to go 1.77 and D for day. But note that 24 hours is in one day and 3,600 seconds are in 1 hour. Meaning then that days and hours would cancel off. I will have seconds. And I might as well look here at the units. Putting the units over here then, it looks like I would have something on the top which would be meter cubed, but there's a meter squared right here, so I'm going to leave a meter on top. This kilogram squared would be flipped and moved up, and this second squared would remain. And then I want to take that Newton and convert it into a kilogram meter per second squared. So that second squareds cancel off. One of the kilograms cancels off with one on the bottom. Meters cancel off. And not a surprise, we're left with units of kilograms, which we should. All right, so the units look great. My unit analysis is working well. Let's put in our numbers. So I've got 4 multiplied by a pi squared, multiplied by a 4.22 times 10 to the 8th raised to a power of 3. Maybe I'll just hit enter with that, because then that is divided by 6.67 times 10 to the negative 11. That then is divided by all these multiplied together and squared. I'll just do them individually and put the square on each of them. So divided by 1.77 squared, divided by 24 squared, and divided by 3,600 squared. All right, so this comes out to be 1.90 times 10 to the 29th kilogram. So again, looking at motion, and because motion is dictated by the gravitational force, which depends on mass, we should be able to get the mass of Jupiter. And I hope I did it right, but it does say go ahead and compare your results. I didn't see the results in your book, so I grabbed a different book here. And it's got the solar system data. And let me just scroll down here. Jupiter, 1.9 times 10 to the... Oh. Now that says 27. 27. Interesting. Let's just check the formula here. I see it right away. 3,600. I typed in only, well, I was 10 times too shy. So let me divide that by a 10 squared. Okay. Oh, that's not quite what I wanted to do. Sorry. So I was off a little bit. Let me just edit it. How about that? All right, let's come back over here. And see if we can do better. Okay, so I think all that's good. Maybe I better come back here and check all my numbers. Oh, and then it has answer. Okay, that's a mistake. So let's try this. Let's take the answer that I did get, copy it. Okay, then let me divide that because I was 10 and squared off. And there we go. So just a little typo there, but glad I saw it. Okay, good. So there is the mass of Jupiter, and it does match. Nice. Take care.